In the name of God, welcome back to Farkhwa's website. My name is Masoud. I'm a physics teacher. Actually, in previous lectures, in previous lessons, we explained centripetal acceleration and we proved the direction of centripetal acceleration, which is directed toward the center of a circular track. Or we can say it has a radial direction. It means the direction of centripetal acceleration is parallel to the radius of the circular track. In this lesson, let's say I prepared the differences between centripetal acceleration and tangential acceleration. So I prepared a table for you. I focused on the main differences between them. After that, I prepared let's say, I focus on a comparison between between AC and AT. Right now, let's say read the first one: differences between centripetal and tangential acceleration. Differences between AC and AT. So this column is dedicated for AC, and the right part of this table is dedicated for AT or tangential acceleration. For centripetal acceleration or AC, I can say the time rate of change or variation. Variation means change. The time rate of the variation of the direction of velocity when it moves on a circular path, right? So this is the first one, the time rate. Just write the definition of centripetal acceleration. What is it about the tangential acceleration? Write the definition for tangential acceleration is the time rate of the change in the magnitude of velocity. Magnitude of velocity means speed, right? And we mean actually VT. Means, let's say, change in delta V leads to what? Leads to change in delta VT, actually. Change in VT leads to AT. The second, let's say, difference, let's say, of AC. AC directed toward the center of a circular track. AC directed toward the center, like this, right? If there's a particle, for example, there's a particle here. This particle, let's say, the acceleration of this particle points toward the center. This is the AC. On this figure, on this, let's say, diagram, I want you to determine the direction of AT for me. And it's clear from its name. I'm sure you know the answer. So direction of AT directed along the tangent to the circular track, like this, right? This is AT, you see? So which type of relationship is there between AT and AC? Are they parallel or perpendicular, right? Leave it for, let's say, just think about it. I'll mention it actually in next subject. I'll mention this one, and I want you to think about it. Let's say, and guess the direction between AC and AT in advance. The third definition, centripetal acceleration or AC, found by what? Found by this equation. AC is equal to VT squared over R, right? VT squared over R, and AC is equal to R omega squared. Teacher, where does, for example, this rule come from? Where does this one come from? In our textbook, it doesn't, let's say, prove it for us. It just, let's say, write the direction, write the equation directly. That's why you are not actually supposed to know the proof, actually. But I wanna, let's say, prove this one for you. The origin of the second equation is the first equation. AC is equal to R omega squared. And actually, in next subject, I'll prove it for you. Let's just focus on the equation only without proving. So AC has two equations. Either you use VT squared over R or R omega squared based on the information within the question. The third differences between them, actually, AT is found by R omega, R alpha. AT is equal to R alpha. What do you say about the fourth difference between them? The fourth one, always, look here, AC always exists in a circular path. I told you. Without actually any exception, without any condition, when the object enters the circular track, so automatically the object, let's say, picks up centripetal acceleration automatically. But what do you say about the tangential acceleration? Tangential acceleration depends on the magnitude of velocity. It depends on the VT. It depends on the speed, right? Whether the object speeds up or slows down, AT creates, right? But let's say AT is created, tangential acceleration is created in the case of increasing or decreasing, let's say, speed. In the case of speeding up or slowing down, AT is, let's say, appeared. But in one situation, AT becomes zero. In which situation? I want you to guess this situation, this condition, when the object moves with a constant speed, when the object moves with a constant tangential velocity. In this situation, AT becomes zero. So AT, let's say, can be zero, no problem. But AC, I keep in mind that AC never becomes zero. A tangential velocity or tangential acceleration or AT, tangential acceleration or AT exists only when speed changes. That's it. In the case of changing speed, AT is, let's say, created. I have a question for you before I go to the comparison between AT and AC, and I want you to guess the answer. And we have it in the question of chapter review in our textbook. Is it possible for AC to be zero or not, and why? The second part of this question, is it possible for AT to be zero or not, and why? Right? Think about these, let's say, questions, and they are very important. I have seen these questions in a multiple choice in national exam. Actually, I'll explain for you in next subjects. Let me read another table for you. The table actually is dedicated for what? This table is dedicated for comparison between AC and AT. Comparison is similarity. Actually, there are two similarities between AC and AT. The first one, they are both linear speeds. So both of AC and AT are linear speed. They belong to linear speeds. Both of them are expressed in meter per second squared. So there are two similarities, right? There are two similarities in this situation. I can say this is a circular track. This is an object. The object, let's say, circles the circular track. And this one is AC, points toward the center. And this acceleration is AT. Both of these acceleration, AT and AC, belong to what? Belong to, let's say, linear accelerations. And both of them are measured in meter per second squared. Actually, I prepared another table for you. This table, let's say, concentrates on what? It concentrates on the rules related to centripetal acceleration. All of the rules that are related to centripetal acceleration, the left part of the table, let's say, focus on what? Focus on VT and AT. So it focuses on the left part of this table, focuses on the rules that include what? The rules that include VT and R. So we have some rules in terms of what? In terms of VT and R. For example, AC is equal to VT squared over R. This is the main rule. The main rule of centripetal acceleration. I'm just gonna read this one firstly. After that, I move to the, let's say, second column, right? So this is the main rule. AC is equal to VT squared over R. I want you to rearrange the equation for VT. So VT becomes what? Let's say use a cross multiply the fraction. Because VT is square, that's why whenever you want to remove the exponent, you have to write the radical, and R and AC multiply by one another. They are multiplied by one another under the radical. So VT is equal to radical RAC. This is the rule for finding VT, right? The third one, what happens when the question actually, when in the question, let's say, when in the question R is unknown, right? So we look for R right now. I want you to rearrange the main equation. When you rearrange it, so AC goes to the denominator and VT squared goes to the numerator. And this is the form of the R. R is equal to VT squared over AC. It's used to find R. This is about the, for example, the rules of AC, including VT and R. Rules, let's say, of AC, right? The rules that have to do with AC, including omega and R. So R is common factor here, R. R is repeated in both types of, let's say, equations. But here, let's say, omega replaces VT. In the second column, omega replaces VT. So AC is equal to what? AC is equal to R omega squared. Is used to figure out AC. So AC is equal to R omega squared. I want you to, let's say, take out the omega, rearrange the equation for omega, and omega is squared. You have to remove the exponent. How do you remove the exponent? By putting the, let's say, by putting the fraction under the radical. Why this, let's say, rule becomes a division actually, or why do we have a fraction here? Because we look for omega, and omega is a variable. Anything multiplied by variable goes down, and the other part goes up. That's why omega becomes radical. AC over R is used to find omega. The third equation has to do with the omega and R. We look for R right now, right? Go back to the original equation. R, I want you to figure out, let's say, figure out R for me. I want you to, let's say, write an equation for R. So which one goes down? Of course, omega squared, it goes down, and AC goes to the numerator. That's why R is equal to AC over omega squared is used to find R, right? And here I prepared, as I told you, actually, I prepared the proof. Maybe you say, teacher, no problem, we can memorize this equation. This is the original form of the AC, but where does R omega squared come from? All right, let me, let's say, prove it for you. I'm going to prove this equation for you. So we look for this equation. Start with the main equation of AC. AC is equal to VT squared over R. This is the main equation of centripetal acceleration. Right. Go back to the previous, let's say, equations. Relationship between VT, R, and omega. Is this equation, isn't it this equation familiar for you? VT is equal to R omega. Yes, it's familiar for us. We know this equation. We got it before. So I want you to substitute this value instead of VT. So substitute R omega instead of VT. What do you get? And VT is square. Because VT is square, so put this square here. Let me write it with another color for you. If VT is square, R becomes square and omega becomes square. That's why the new form of the numerator becomes r squared omega squared divided by r. So here, I have a question. Can I, let's say, cancel out 1r with 1r? 1r in numerator and 1r in denominator? Yes, it can be. That's why in this situation, what's the, let's say, what's the other final form of the AC? Final form of the AC in terms of r and omega is this equation. AC is equal to r omega squared. So whenever you look for AC, let's say either you use this equation, which is the main equation, Vt squared over r, right? Or AC is equal to what? AC is equal to r omega squared. We have two forms of AC. This one based on, let's say, Vt and r, and this one in terms of r and omega. Thank you very much, guys, for watching this video. I hope you enjoyed this video, and I want you to follow our next videos on Fermat's application. And bye for now.